So this is the slide I was basically showing you, okay? So again, all we're doing is employing enolates here. And my point is, all we're using enolates as a nucleophile. In chapter 22, we specifically looked at SN2 reactions, and then you guys probably culminate with the malonic ester and the acetoacetate synthesis. In this chapter, we're really just going to explore taking this enolate and reacting it with a carbonyl, okay? Here I'm showing a ketone, and one of the things you should have learned about aldehydes and ketones is that the enolate reacts with a ketone, a nucleophile reacts with a ketone to make a tetrahedral intermediate, where I have 4 groups around this carbon, okay? What I was trying to share with you guys, and again, I can't do this because of my document camera is not working for whatever reason, but this chapter is divided into 2 segments. The first segment is we're going to explore this reaction specifically with aldehydes and ketones, okay? And one of the things you'll recognize is once I form this intermediate, we can attack this O- with a proton to make a beta hydroxy ketone or an aldehyde, okay? That's going to be called the aldol reaction. And then the end of the chapter looks at the same reaction, but instead of using a ketone here, it chooses esters, okay? That's called the Claisen reaction. So the Claisen reaction and the aldol reaction are very similar in that we have a carbonyl system. The only difference is what happens with the tetrahedral intermediate. Remind yourselves that aldehydes and ketones have terrible leaving groups, so we stop here. This guy cannot collapse to the carbonyl because I would leave either with hydride in the case of the aldehyde or an alkyde in the case of an alkyl group here. On the other hand, if this was an ester, I have a pretty good leaving group in that I would regenerate the carbonyl to make to generate the alkoxide as a leaving group. Okay, so again, the only part here is we're going to be looking at this reaction of attacking enolates with carbonyl systems, but recognize there was 2 mechanisms you learned specifically for carbonyls. Aldehydes and ketones do nucleophilic addition, whereas carboxylic acids, and specifically esters, do substitution through an addition followed by elimination mechanism. Okay, kind of ring a bell what Dr. Schwann has taught you guys probably in exam 2.
Absolutely.
Okay, so it's fresh. And so structurally, my lecture notes are specifically designed, and the book is designed to basically have you guys look at these 2 reactions and treat those 2 reactions separately. So the first one that we're going to look at is the reaction of this guy with an aldehyde or ketone. So here, I'm going to basically take 2 aldehydes, okay? And notice these are the same aldehydes. So this is called a dimerization reaction. I'm taking 2 molecules and I'm making a big molecule. If you look at acetaldehyde, this is a C2 carbon, in that I have a carbonyl and a methyl group here. So I have 2 carbons, and I also have 2 carbons here. If they both react with one another, notice I make a 4-carbon species. So this is a dimerization where I've just taken 2 carbons, and made a 4-carbon. And again, this is the simplest example. We will deal with larger examples. So this is one of the most effective ways to make a carbon-carbon bond, okay? It's right there with Grignard reactions, which you already learned, okay? Now, you're learning a bunch of named reactions, and often named reactions are named after people. In the case of the aldol reaction is termed based upon the product of this reaction. Recognize that the al is emphasizing I have an aldehyde in my product. So this is the aldehyde portion. And if you think about how you name alcohols always have an OL. So this molecule is called an aldol in that I have both the functional group of an aldehyde and an alcohol. And specifically, the alcohol is on the beta carbon. Recognize that the most acidic proton is always the alpha carbon. And so I'm going to take this alpha carbon here. At some point, I'm going to deprotonate with strong base. We talked about that. This is basically equilibrium conditions. Once I make that enolate, since enolates are nucleophiles, it can react with this aldehyde, which is an electrophilic center. So basically, if this is an electrophile here and this is a nucleophile, the alpha-beta bond here is formed from a nucleophile reacting with this electrophile. So if you guys want to write, please put down that the alpha carbon is always my nucleophile. And it's always going to be adjacent to the carbonyl. The beta carbon, on the other hand, is always going to be my electropositive center. And that's going to be the center in which I attack the nucleophile to the beta carbon, which is electrophilic. So this is forming a bond between a nucleophile and an electrophile. Alpha being the nucleophile, beta being the electrophile. Okay? Now, I wanted to do this mechanism with you guys on the digital document camera. I apologize I don't, but it's pretty simple. I'll try to go through it a little bit slower with you. So the first step in this mechanism is that we first basically take the aldehyde and we're going to treat the aldehyde with the weak base. Okay, the most acidic proton on aldehydes, once again, is the alpha carbon, shown here. I'm going to basically take hydroxide, abstract this proton at the alpha carbon, and get this enolate. Okay, that's all we've been doing this morning. Now that I have this nucleophile, I'm going to treat this nucleophile with a second molecule of aldehyde that now is going to react as an electrophile. So notice that this portion has not been deprotonated. So again, this part here is going to be my electrophilic carbon. I'm going to take this nucleophile, attack it here through nucleophilic addition, and again, I'm going to form the tetrahedral intermediate. Okay, so that's kind of what I showed you in the preceding slide, right? All we did was show how to make the enolate, and then this enolate reacts with ketones or aldehydes to get the tetrahedral intermediate. That's all I did. So this is step 1, this is step 2. Okay, so now that I have this tetrahedral intermediate, the last step here is basically the alkoxide that's formed, this tetrahedral intermediate oxygen that has a negative charge, reacts as a base with water in this case. So whatever the conjugate acid that's formed in this reaction, in this case, if I'm using hydroxide, it's water. If this was ethoxide, it would be ethanol. Whatever the conjugate acid is, I'm going to use that to make the beta hydroxyaldehyde. Okay, so basically I'm going to form, the first step is an acid-base reaction to make the enolate. Then I have nucleophilic addition in step 2. And step 3 is another acid-base reaction. Very simple mechanism. Okay. Product is, once again, called a beta hydroxyaldehyde. Okay. Now, it turns out that I could also, in some cases, I could dehydrate this alcohol. Okay. So if you look at this, I have an...
Can you please go back?
Yeah. You have a question?
Professor, would you use 2 equivalents or excess of the aldehyde in this case to form the aldol product?
Well, does it matter? So what was my notes that I did on a pen and pencil at the beginning? I talked about equilibrium, right?
Oh, true. Yeah. Okay.
Right. So
yes,
how much aldehyde or ketone would you form with hydroxide? Less than 1% enolate. Right? So once we form a little bit of enolate, it's going to find a large excess of the aldehyde.
Yeah. Okay.
Okay? Because again, it's under what? Thermodynamic conditions. It's under equilibrium conditions. Okay? So notice that's a great question. Notice that's why in all these arrows, I want to emphasize this. That's why we're using the equilibrium arrows. They're all reversible reactions. Okay? Great question, though. I didn't even think about it, put in that context, so thank you about that. So again, the question is, do we need to use a large excess of base, of aldehyde? No. Again, because we're using a weak base, most of this equilibrium is shifted to the left, okay? Again, that table that I made you guys was basically, we only have 1% of this formed with the weak base, such as such as sodium hydroxide. Okay. Now, we can also dehydrate the aldol product. Okay. So notice I have an alpha hydrogen here, and I can also have OH here. So if you think about it, water is H2O. Here I have an OH, and here I have an H. So I can, if I lose this guy here, I make water. Okay. Well, it turns out I could dehydrate that. Dehydration of an aldol product makes what we call an alpha, beta, and saturated system. Okay, specifically here, I'm making an alpha, beta, and saturated aldehyde. So here I have a carbonyl. This is my alpha, and this is the beta. The alpha and beta is called unsaturated because I made a double bond. It turns out the mechanism for this reaction is new. Okay, recognize that once I make this product here, hydroxide still finds the fact that I still have a relatively acidic alpha hydrogen, right? And so I'm going to basically take this proton and abstract the alpha proton here to generate a new enolate. Okay? And the thing about enolates, they're what? They're stabilized by what?
Resin.
By resonance, right? So by resonance. So the bottom line is, in order to dehydrate this, okay, I'm going to form the enolate here. And then once I form the enolate, I'm basically going to have hydroxide become the leaving group. So here I have a double bond being formed with this electron being pushed onto here with this OH group leaving. Okay, this is a new mechanism. This is basically an elimination mechanism. And in the first semester, you should have learned two elimination mechanisms. You learned E1 and E2. E2 was what? A concerted reaction, right? Where I take the base, and as the base is reacting, the leaving group leaves. But in E1, I formed an intermediate where I formed a carbocation. Okay? The reason this is called E1CB is rather than form a carbocation here, I'm forming a resonance stabilized carbanion. So again, this is a new mechanism. It's called E1CB. Hydroxide's first abstracting the proton at the alpha carbon because that generates a resonance stabilized carbanion. Okay, this carbanion is stabilized through resonance, and at some point it will subsequently eliminate an OH to form the alpha, beta, and saturated system.